Hi everyone, this is Kevin Brown. We are in chapter 12. This is an exciting chapter. Now you probably wouldn't think that for any chapter of a stats book, and maybe I'm just a little bit different. In fact, I know I am. But I think most people would really enjoy this chapter because it introduces simple linear regression. And what are we doing in simple linear regression, or any regression for that matter? We're trying to draw relationships. We're trying to draw some associations. So this is exciting material. This is something that is one of the major usages, major tools, I should say, utilized in research, statistical analysis, and answers a host of questions. So for example, if you went into Google News, threw in multiple regression, you're going to find thousands and thousands of studies, articles being done where someone was able to determine something interesting or make some kind of interesting statement about phenomenon using the tool of regression. So here in chapter 12, I've broken this up into two parts, kind of a part A and part B. And we're going to go through this, and I'm going to show you some of the components of simple linear regression. And when I talk about simple regression, that just simply means that there's one variable that's doing the explaining, and there's one variable that's being explained. So let's talk about this. This involves, as mentioned, one independent variable. This is the variable doing the explaining. We sometimes call this the explanatory variable. And this is notated as x. And recall that x is the horizontal line in that two-dimensional xy graph. And the dependent variable, the variable that's being explained, is the y variable. And typically this variable will be on the vertical axis. And the relationship between the two variables is approximated by a straight line. So when we're doing linear regression, we're trying to approximate a relationship using a straight line. Now, there can be two variables that have a relationship where the relationship is not approximated by a straight line, yet does reveal a relationship, and this is just simply nonlinear regression. I have some slides that explore that later on, but for now, we're just simply looking at simple linear regression. So at the bottom of this slide, I've got a student here who's obviously kind of conked out, and let's imagine that I was interested in the relationship between number of hours or average hours per night that a student gets rest and their performance in the classroom. We might call this GPA. So what would my x variable be, and what would my y variable be? Well, the variable that's doing the explaining in this example would be sleep, average hours of sleep. So my x variable would be sleep, and my y variable would be classroom performance. How does sleep affect, what is the relationship between sleep and classroom performance, or in more technical statistical jargon, how does the variation in x explain the variation in y? And obviously, if we're using more than one variable to explain that y variable, we call this multiple regression, which we'll take up in chapter 13. So here is the simple linear regression model. We have y, which is our dependent variable, as I just said, is equal to b sub 0, and this b sub 0 is referred to as our y-intercept, plus b1, that is our slope coefficient, and that is a slope coefficient on x, which is our independent variable or our explanatory variable. Now, when we're talking about the model, we write this plus e, where e is referred to the error term. These are the things that aren't captured necessarily in x. This is our error. So when we're talking about regression lines, we're really talking about three different kind of potential lines. The first is what we would understand as a positive linear relationship there in panel A. The second would be a negative linear relationship. There is a relationship, but it's negative. And panel C would be there's no relationship. And if there's no relationship, our slope is going to be 0 or very close to 0, a flat line. There's no slope. So some examples of this, a positive linear relationship, we might say age explaining height, at least within a certain age range. So as you're getting older, you're getting taller. Negative relationship would be age explaining metabolism. perhaps in a different age range. As you're getting older, your metabolism is going down. So there's a negative relationship. But what about something that doesn't have any relationship? Well, if I collected data on age and use that to explain rainfall, I would likely, in case there was some spurious correlation, have a very flat line. Someone's age or the mean age or median age or anything like that does not explain rainfall. There is no relationship between the two. So I want to take a moment and talk about cause and effect, and I may actually make a separate video related to this because trying to understand relationship can be a very tricky thing. But when we're doing regression, that's precisely what we're looking at. We're looking at relationship. We're looking at association. We're looking at correlation. But this is often mistaken as cause and effect. And there are lots of reasons that, again, I may get into in a separate video, why we want to avoid this kind of language. So just to give one simplistic example, suppose I'm interested in the relationship between the percentage of employers in a given metro area that are considered to be Fortune 500 companies and the percentage of individuals within that area that have college degrees. Now, intuitively, I would suspect that there is a correlation between the two because large employers who often value college education may want to locate to areas where there's a population of individuals who are college educated. So suppose I did find a strong relationship, why would I say that the two are positively correlated and not college degrees cause Fortune 500 companies to flock to the area? Well, first, we'd have to control for every single factor that motivates a company to move to a specific area, and this would be nearly impossible and may vary from employer to employer. So in one sense, there might be a relationship or a causal effect, but we don't know the degree of that real effect until we control for all of the other factors that explain the variation why companies move to the places that they do. Second, we don't know the direction of causation. Employers may move to areas where a large percentage of the population is educated, or conversely, educated people may move to areas where there are a lot of jobs demanding a college education, Fortune 500 companies. So we don't really know what the causal direction is, or are the two actually even causing each other or reinforcing each other, what some have referred to as mutual endogeneity. So I just wanted to take just a moment, and you've probably heard this phrase, certainly if you've had any exposure to statistics, that correlation is not causation, and this is just one example why. It can be, but what we're doing in regression, simple regression, multiple regression, doesn't necessarily tell us a causal mechanism unless we do a few unique things with the data, which I won't get into at this point. All right, back to our data. Let's take a look at a data set here. This is the student population and then quarterly sales for this pizza place, Armand's Pizza. And you can see that the X variable is student population, and then we're looking at the Y variable, quarterly sales. And notice, too, how the units are expressed. So 2 is 2,000 because they're expressed in thousands, and 58 is 58,000. So if my X variable is student population, my Y variable is quarterly sales, what does that mean? It means I'm looking at how a student population correlates or influences or affects the variation in quarterly sales. Presumably, as the student population goes up, my sales go up because students like to eat pizza. I know I certainly did. But we'd want to actually do a test to see what the true nature of the relationship is. Now, before doing more granular numerical statistics with this, oftentimes we can just simply conduct a scatter plot and visualize the nature of the relationship. So I've done that here. You can see student population, the X variable is on the horizontal axis. Quarterly sales, the Y variable is on the vertical axis. And we can see as our student population goes up, our quarterly sales go up. And so it appears that there is a positive linear correlation. I say linear because we can approximate this relationship by a straight line. Not all the points would fall on that line. We'll talk about that in a moment. But we can draw a line right up through this data. So just giving this the eyeball test, I can immediately see that there appears to be a strong positive relationship between the student population and quarterly sales for pizza. Now, I mentioned this line earlier that would go through this data, and this is really a part of a larger method we're using, which is called the least squares method. And basically what we're doing here is we're drawing a line of best fit through the data. It's actually the line that minimizes the sum of squared errors. Now, if you're like, I don't know what you're talking about, that doesn't make any sense. Basically what it is it's drawing a line through this data in such a way that minimizes the distance between all of these little dots, all of these observations, and that line. It's the line that best fits the data. So when we're doing the least squares method, that's actually what's taking place. So we've got a couple of different things that we can find. The first is the slope coefficient, if you recall our actual regression equation. And this is the slope coefficient on the x variable. And here we need to find the sum of xi minus x bar times yi minus y bar. And we're going to divide that by the sum of xi minus x bar squared. May make a separate video. In fact, I know I have a separate video on what this actually looks like. So that is our slope. And once I've found my slope, then you can find the y-intercept. Now, really quick, what is the y-intercept? It's just simply where that line of best fit intercepts with the y-axis. So in this example below, it intercepts at 2. So that means if our x value is 0, you're basically multiplying 0 times the slope, which is 0. This is where you would be. You'd be at 2. And our formula for this is b sub 0, our y-intercept, is equal to y bar minus the slope times x bar, the mean for x, the sample mean for x. So the sample mean for y minus the slope times the sample mean for x. So once you figure out slope, finding this out is pretty simple. Now, here's just an example of what this looks like, and I'll allow you to kind of pause the video, take a look at this. As I mentioned in one of my earlier videos on doing the standard deviation, yeah, can you skip a few steps and do this in a little more of a simplistic way? Absolutely. The reason, though, that this method is preferred, if you're doing it by hand, is because it's so much easier. Not only is it so much easier, but it allows you to kind of follow through, see where you may have made a mistake, and it allows you to kind of take a systematic approach to figuring this out. Now, here's our line of best fit where we've solved for our slope and we've solved for our y-intercept, and we see that y hat, notice that hat means our estimated value of y, is equal to 60 plus 5x. So let's interpret this. Now, on the next slide, I'm going to interpret the slope coefficient, but let's think carefully for a moment about what that 60 means. So on a technical level, or in a technical sense, that is where our line of best fit intercepts with the y-axis. And you can see it intercepts at 60. So what does that actually mean? How would we interpret that insofar as understanding the relationship between student population and Armand's Pizza? Well, it means that if the student population was 0, if x were 0, then 0 times 5 is 0, and all there is 60. So another way of saying that is, if Armand's put a pizza parlor in a place where there were no students, he or she would still sell about $60,000 worth of pizza in a quarter. So if x is 0, then you still have a value of 60. Now, what does the slope coefficient mean? What I tend to ask my students to do is actually write this expression down. And I would strongly encourage you to do the very same thing, whoever's watching this video. Write this expression down. For every 1 unit increase in x, we see a blank unit increase or decrease in y. So for every 1 unit increase in x, we see a blank, and there you would just simply write in the slope coefficient unit. How do I know if it's an increase or decrease? I look at the value on that slope coefficient. Is it positive or is it negative? If it's positive, it's an increase. If it's negative, it's a decrease. We see a blank unit increase or decrease in y. So what does this mean for Armand's Pizza Parlor? Remember that my slope coefficient was 5. Well, on one level, I need to go back and look at the units. And remember, the units were expressed in thousands, so that 5 would actually be a 5,000. So for each 1 unit increase in the student population, that's my x variable, in the thousands, so if the student population goes up by 1,000, I would see a 5 unit increase in sales. So if the student population goes up by 1,000, I'll get $5,000 of an increase in sales. And that is how we interpret the slope coefficient. So again, I would encourage you to remember this particular expression. So I can take any data and, using that aforementioned formula, construct an estimated regression equation by estimating the y-intercept and the slope coefficient. However, this does not tell me, is it a good estimate? Is the x variable actually explaining a lot of the variation in y? Does x explain y well? Or in the case we looked at, does student population explain pizza sales pretty well? Well, looking at the scatter plot, it seemed like it did, but we can actually determine a specific value, what's called the coefficient of determination, or it's more commonly referred to as r squared. And when we're doing our r squared, it's a value between 0 and 1. And the closer you are to 0, that means it's not explaining a lot of the x is not explaining a lot of the variation in y. And the closer it is to 1, that means it's explaining a lot of the variation in y. And it's a percentage. So let's say it was 0.75. Then we would say 75% of the variation in y is explained by x. So to do this, we need to know 3 things: the sum of squares due to error, what's called SST, total sum of squares, and then SSR, sum of squares due to regression. This is, when we do this in Excel, obviously Excel will do this for you, but I simply want to go through kind of the mechanics of what we're looking at. So here are the formulas for each of these, but notice that our SSR and our SSE, sum of squares due to regression, the amount that is explained, and sum of squares due to error, the amount that's not explained. When you add those two together, we get the total sum of squares. Now below here you see, what is y hat? Well, recall that I said y hat is estimated y. And how do we find it? We would just simply take the actual regression equation, plug it in, and then we would plug in the x values in order to find that y hat. So by plugging in each xi value into our regression equation, we can figure out y hat. So you'll see in this particular example, the y hat column under predicted sales, expected y, is equal to 60 plus 5x, so that's our regression equation. But notice that I'm just plugging in x, or the x value from that first row under student population into this formula. So for example, in restaurant number 1, the student population is 2 or 2,000, and so I would plug that into the x under y hat is equal to 60 plus 5x. So 5 times 2 is 10, plus 60 is 70, and you see that's the value below. Or if you go down to restaurant 4, it's 8. 8 times 5 is 40. 40 plus 60 is 100. The second thing I want to point out is just simply the error, and the error is going to be yi, our actual y value, minus our expected y value, and how different those two are is what we call error. And we need to know that in order to determine the sum of squares due to error, which you see in the bottom right-hand corner of this particular table. So if we figure out this total sum of squares due to error, if we do the same thing with sum of squares due to regression, we see that that's 14,200. And recall that adding the two of these together will give us SST, the total sum of squares. So you're probably thinking, who cares? Why is this important? What does this have to do with r squared? What it has to do with it is r squared is equal to the sum of squares due to regression divided by the sum of squares, the total sum of squares. And so once we find out SSR and find out SST and divide the two together, this actually gives us our r squared value. And if we go back to Armand's Pizza, we see that SSE is 1530, SSR is 14,200. When you add the two of those together, you get 15,730. So our r squared is taking the SSR 14,200, dividing by SST 15,730, and we see that that is 0.90 or 90%. 90% of pizza sales can be explained by the student population. And that is an example then of our R-squared. Here's just one more example. I would invite you to maybe try this on your own. And in a separate video, I'm going to show you how to use this particular data set in Excel. So obviously doing this by hand is a little more cumbersome, but the value is you gotta get to pop the hood, if you will, on this, see how it works, see what's actually taking place statistically. But utilizing Excel is much more elegant as well. We'll talk about what that looks like, how to do it, etc. in just a little bit. All right, this is part A of chapter 12, and look forward to the next video, part B of the same chapter. Thank you.